So far, we have been operating under the idea that under a rotation of coordinates given by r n hat theta, that is a rotation through an angle theta about the axis n hat, the ket describing a quantum system changes from the ket psi to a new ket which is obtained by an operator un hat theta acting on psi. What we did not perhaps explicitly say here is that we consider in this picture only the states to change under a rotation of coordinates, while the operators do not change. Note, however, that in quantum mechanics, matrix elements of operators psi or phi have physical significance, not the kets and or the operators on their own. So, the same physics can be described in an entirely different manner. Instead of the kets changing and the operators staying the same, we could also think of an approach where the kets stay the same while the operators change by this rule. Whereas the kets were changing by, in our previous approach, kets were changing by un hat theta acting on psi. Here the kets don't change, but the operators change by un dagger theta o hat un theta. Notice that in both of these two approaches, the way in which the matrix elements change is the same. That is, psi o phi changes to psi un dagger theta o hat un theta phi. In the second approach, this is obvious because this, of course, is a changed operator after the rotation of coordinates. Psi and phi is the same. In the previous approach, the ket phi here becomes this new ket. The bra psi, which is sitting on the left of this matrix element, changes in a manner which is dictated by the change in the corresponding ket. Whereas the ket psi would have changed by un theta psi, or changed to un theta psi, the bra psi would change to bra psi un dagger theta. So in both approaches you end up with the same result. Note that there is a chance that you might confuse these two approaches with a change of picture, where both kets and operators transform, keeping the matrix elements unchanged. In a sense, there is a change of picture involved here, that is, between this approach and this approach, there is a change of picture. I will let you figure out what is going on exactly there. But you have to remember that in our situation, between the original ket psi before the coordinate rotation and the new ket psi tilde, un hat theta psi, you do expect the matrix elements to change because something has really changed in the physical system. Let us now consider a situation for a very special class of operators, so-called scalar operator, one for which matrix elements do not change under rotation. Such an operator S hat standing for scalar operator, must obey un dagger theta S hat un theta. The changed operator must be the same as the original operator S hat. That is to say that any scalar operator commutes with a rotation operator. S hat un theta commutator must be 0. And if you consider an infinitesimal version of the rotation, then this un hat theta operator must be identity plus I epsilon by h cross n hat dot j, and this must vanish since S hat commutes with the identity, and this is true for all epsilon. You must have this rather important result, that a scalar operator commutes with j vector, which means it commutes with each and every component of j vector. A very special case, very important special case, happens to be a Hamiltonian for a system which has rotational symmetry. If you have rotational symmetry, of course, the Hamiltonian cannot change under rotation, and then the Hamiltonian must commute with all the components of angular momentum. This actually is a very important result, and it helps to simplify the calculation in a big way for many spherically symmetrical system. Of course, it might so happen that a system does not have full rotational symmetry, but has symmetry only about one axis of rotation, in which case the Hamiltonian actually commutes with the angular momentum component only in that direction. This is also easy to understand because in this particular case, if you have rotational symmetry about the z-axis, Jz is exactly the operator which generates rotations about the z-axis. So Hamiltonian must commute with Jz.